Nice to see you again. Let's move on to the next section, which covers questions 21 to 40 of the Generative AI Multimodal NCA-GENM certification. Question 21. You are using a multimodal generative AI model that integrates both text and image inputs to generate detailed product descriptions and corresponding visuals. However, you observe that the generated images are high quality, but the textual descriptions are vague and lack detail. What could be the primary cause of this issue? The image encoder is not properly aligned with the text encoder. B. The model was not trained for enough epochs. C. The text data used for training was not sufficiently diverse or detailed. D. The learning rate used during training was too high. Okay, so the problem here is an imbalance in the quality of the model's output. It's a great artist, producing high-quality images, but a poor writer, producing vague text. We need to figure out why one skill is strong while the other is weak. Let's look at the options that would likely cause problems for both the text and the images. Option B, not training for enough epochs, and Option D, using a learning rate that's too high, are general training issues. They would likely prevent the model from learning effectively overall, resulting in both poor images and poor text. Option A, a misalignment between the encoders, would mean the model can't connect the right text to the right image, which would also likely degrade the quality of both outputs. These don't explain the specific imbalance we're seeing. This makes Option C the most logical and primary cause. The text data used for training was not sufficiently diverse or detailed. This is a classic example of the garbage in, garbage out principle. A generative model learns to create outputs that mimic the quality of the data it was trained on. Think of it this way. If you train the model on a dataset of beautiful high-resolution photographs, it will learn to generate beautiful high-resolution images. But if, for that same dataset, the accompanying text descriptions are all simple and vague, like a red car or a person walking, the model will only learn to generate simple and vague text. It can't create detailed, rich descriptions if it has never seen them during its training. The fact that the images are good while the text is bad strongly suggests the training data for the image part was excellent, but the training data for the text part was poor. Question 22. A healthcare company is developing a generative AI system that can analyze multimodal data, including medical images, X-rays, patient history, text, and lab results, numerical data. The goal is to generate detailed reports that can help doctors make more accurate diagnoses. Which technique is most appropriate for integrating these diverse data types to generate comprehensive diagnostic reports? Use a convolutional neural network, CNN, for all data types. B. Use a GAN to generate synthetic data for each modality before analysis. C. Implement a multimodal fusion strategy that combines data representations from CNNs, RNNs, and dense layers. D. Rely solely on a transformer model designed for text data. Okay, the core of this question is about system design. We have three very different kinds of data: images, text, and numbers, and we need to build a single system that can understand all of them together to make a smart decision. The key is to use the right tool for the right job. Let's look at the incorrect approaches first. Option A suggests using a CNN for everything. CNNs are specialists at processing images, but they are not the right tool for understanding sequential text or simple numerical data. That would be like asking a radiologist to also interpret patient interviews and financial records. Option D suggests only using a transformer model for text. This would mean completely ignoring the X-ray images and the lab results, which would obviously lead to a very poor and incomplete diagnosis. Option B, using a GAN, is also incorrect because GANs are for generating new data, not for analyzing and integrating the existing data you already have. This makes Option C the correct and most effective strategy. Implement a multimodal fusion strategy. This is the standard team of specialists approach. You use a CNN, which is the expert at understanding images, to analyze the X-rays. You use an RNN or a transformer, which are experts at understanding language, to process the patient's history. You use simple dense layers, which are good at handling structured numbers, to interpret the lab results. Then, a fusion strategy takes the intelligent summaries from each of these specialist models and combines them to form a single, comprehensive understanding of the patient's case. This allows the system to generate a final report based on all available evidence. It's the most robust and appropriate way to handle diverse, multimodal data. Question 23. You are developing an end-to-end customer service chatbot for a retail company using NVIDIA Riva. The chatbot pipeline includes ASR to transcribe customer speech, NLP to interpret and respond to queries, and TTS to generate spoken responses. What is the best approach to ensure that the chatbot provides accurate and contextually appropriate responses? A. Fine-tune the NLP model on a dataset containing typical retail customer inquiries. B. Train the ASR, NLP, and TTS models separately on unrelated datasets. C. Deploy the TTS model with a focus on speed rather than naturalness to ensure fast responses. D. Use a general-purpose ASR model without domain-specific fine-tuning. Okay, so this question is about making a specialized chatbot smart. The pipeline has three parts: the ears, ASR, the brain, NLP, and the mouth, TTS. The goal is to make the chatbot's answers accurate and relevant to a retail store. This means we need to focus on making the brain of the operation as smart as possible about retail. Let's look at the options that don't achieve this. Option B, training on unrelated datasets, would be a complete failure. You can't train a retail chatbot on medical texts and expect it to work. Option C is about the TTS model, the mouth. Making the voice faster but less natural doesn't make the content of the answer any better. Option D is about the ASR model, the ears. While a specialized ASR is helpful, even if it transcribes a customer's question perfectly, the chatbot will still give a bad answer if its NLP brain doesn't understand the retail context. This makes option A the best and most direct approach. Fine-tune the NLP model on a dataset containing typical retail customer inquiries. The NLP model is the core component responsible for understanding the user's intent and formulating a response. A general NLP model might know what a return is, but it won't know your company's specific 30-day return policy. By fine-tuning the model on a specialized dataset of real retail questions and answers, you are essentially giving it on-the-job training. It learns the specific vocabulary, like SKUs, order numbers, brand names, common problems, and correct policies for that retail environment. This is the most critical step to ensure the responses it generates are not just grammatically correct, but also accurate and contextually appropriate for a customer service interaction. Question 24. You are customizing a pre-trained multimodal model to create an interactive application that can generate descriptive text from images, transcribe audio, and classify text documents. Which method would best allow you to leverage a single model for these diverse tasks? A. Use an encoder-only model like BERT and extend it to handle image and audio tasks. B. Use a pre-trained multimodal transformer like DAL-E, which can be fine-tuned for text, images, and audio tasks. C. Use a sequence-to-sequence model like T5 and add image and audio processing capabilities. D. Utilize a pre-trained multimodal model like Florence that can handle multiple data types and fine-tune it for specific tasks. Okay, so the core of this question is about choosing the right starting point. We need a single AI model that can act like a Swiss Army knife, performing 3 different jobs: describing images, transcribing audio, and classifying text. The key is to find the most efficient and effective foundation to build upon. Let's look at the options that are not ideal. Options A and C suggest starting with powerful text-based models like BERT or T5, and then adding on image and audio capabilities. This is like starting with a really good knife and then trying to bolt on a screwdriver and a pair of scissors yourself. It's possible to do, but it requires a lot of difficult custom engineering, and the final result might be clumsy because the tool wasn't originally designed to do those other things. Option B suggests using DAL-E. DAL-E is famous for one specific task: generating images from text. Using it for audio transcription or text classification would be like trying to use a paintbrush to write an essay. It's a highly specialized tool and completely wrong for the other jobs we need to do. This makes option D the best and most logical answer. Utilize a pre-trained multimodal model like Florence. Models like Microsoft's Florence are designed from the ground up to be multimodal. They are pre-trained on massive datasets containing text, images, and other data types all linked together. This means they already have a unified architecture for understanding how different types of data relate to each other. Starting with a model like this is like buying a high-quality Swiss Army knife that already has all the tools you need built in from the factory. Your job is then much simpler. You just need to sharpen the specific tools you need for your application through fine-tuning. It's by far the most effective and efficient approach when you need one model to perform diverse tasks across multiple modalities. Question 25. You are optimizing a generative AI model's performance by tuning hyperparameters. Which of the following strategies is most likely to improve the model's training efficiency without compromising its ability to generalize? A. Reducing the batch size. B. Increasing the learning rate significantly. C. Using a lower precision for computation. D. Applying regularization techniques. Okay, this question is looking for a win-win scenario. We want to make the training process more efficient, faster, or using fewer resources, but with the strict condition that we don't hurt the model's ability to perform well on new, unseen data, which is called generalization. Let's first look at the options that don't fit. Option A, reducing the batch size, often makes training less efficient on modern hardware like GPUs, which are optimized for parallel processing on large batches. Option B, significantly increasing the learning rate, is very risky. It can cause the training to become unstable and prevent the model from learning properly, which would definitely compromise its ability to generalize. Now let's compare the two plausible options, C and D. Option C, using a lower precision for computation, like mixed precision training, is a very powerful technique for improving training efficiency. It makes calculations faster and uses less memory. However, it comes with a small risk of slightly affecting the model's final accuracy, so it could potentially compromise generalization, even if it often doesn't. This makes option D, applying regularization techniques, the best answer. Regularization methods like dropout or L2 regularization are specifically designed for one primary purpose: to improve a model's ability to generalize by preventing it from overfitting, memorizing the training data. While these techniques might add a tiny amount of computation to each training step, they help the model learn the right patterns more effectively. This means the model can reach a good, generalizable state in fewer overall epochs, which improves the total efficiency of the training process. So, because regularization's main job is to improve generalization, it is the strategy most likely to meet the condition of, without compromising its ability to generalize, while also contributing to overall training efficiency. Question 26. You are working on a predictive maintenance system for industrial machinery, using time series data to predict equipment failures. The dataset contains several features, including temperature, vibration, and operating hours. However, the model's predictions are not accurate, possibly due to the time-dependent nature of the data. What pre-processing step should you take to improve the model's performance? A. Perform feature engineering to create lagged variables. B. Increase the number of training epochs. C. Switch to a deeper neural network model. D. Normalize the data across all features. Okay, the key to this question is in the description of the problem. The model's predictions are not accurate, possibly due to the time-dependent nature of the data. This is a big hint that the model isn't properly understanding the patterns that occur over time. It's only looking at a single snapshot in time, not the sequence of events. Let's look at the options that don't directly address this core issue. Option B, increasing training epochs, or option C, using a deeper model, might not help if the underlying data isn't structured correctly. You can't learn a pattern if the information isn't there to begin with. Option D, normalizing the data, is a very important standard pre-processing step, but it only scales the existing features. It doesn't create new information that would help the model understand time. This makes option A the correct and most effective answer. Perform feature engineering to create lagged variables. This is a fundamental technique for time series problems. A lagged variable is essentially a new feature that represents a past value of an existing feature. For example, you would create a new column in your data called temperature_5_minutes_ago, or vibration _10_minutes_ago. By doing this, you are explicitly giving the model a short-term memory. At any given moment, the model doesn't just see the current state. It also sees the state from 5 minutes ago, 10 minutes ago, and so on. This allows the model to learn crucial time-dependent patterns, such as a rapid increase in vibration over the past 10 minutes is a strong indicator of an impending failure. Without these lagged features, the model has no context of the past and cannot learn these critical temporal relationships. Question 27. Which of the following statements best describes the primary challenge and opportunity presented by generative AI in content creation for businesses? The challenge is producing diverse content quickly. The opportunity is cost reduction. B. The challenge is finding enough data. The opportunity is improving operational efficiency. C. The challenge is integrating AI into workflows. The opportunity is reducing manual labor. D. The challenge is ethical content creation. The opportunity is enhancing creativity. Okay, so this is a high-level strategy question. It's asking us to identify the biggest risk and the biggest reward when a business starts using generative AI for creative work like writing articles or making images. Let's look at the other options first. Options A, B, and C all state some truth. Generative AI certainly brings opportunities for cost reduction, improved efficiency, and reduced manual labor, and there are challenges with data and integration. However, these points are true for many types of automation, not just generative AI. They are a bit generic. This is why option D is the best answer. It captures the most unique and significant aspects of this specific technology in a creative context. First, the challenge, ethical content creation. This is a massive and primary concern for any business using generative AI. It includes a host of complex issues like, is the AI-generated content accidentally plagiarizing someone else's work? Is the model trained on copyrighted data? Could the AI generate misinformation or content that is harmful or off-brand? These are new, difficult, and high-stakes ethical questions that businesses have to navigate. Second, the opportunity, enhancing creativity. This goes far beyond just making things faster or cheaper. Generative AI can act as a brainstorming partner for a marketing team, help a designer overcome a creative block by generating novel concepts, or allow a writer to explore different tones and styles instantly. The true opportunity isn't just to automate what humans already do, but to augment and enhance human creativity, leading to new ideas and better final products. So, while the other options are valid, option D best describes the most profound challenge and the most transformative opportunity that are unique to using generative AI in the creative process. Question 28. You are developing a multimodal AI system that generates high-resolution images from complex English text prompts. The system must handle a variety of detailed descriptions and produce visually accurate results. What strategies are most effective for optimizing the performance of a text-to-image generation model in handling diverse and detailed English text prompts? Select 2. Implement a separate model for image refinement after initial generation. B. Incorporate a large and diverse set of image-text pairs for training. C. Use a transformer-based model for text encoding. D. Use a fixed text-to-image model without fine-tuning. E. Limit the model's training to simple, short text descriptions. Okay, the goal here is to build a great AI artist that is also a great listener. It needs to understand complex, detailed text instructions, prompts, and turn them into accurate pictures. We're looking for the 2 most effective strategies to make this happen. First, let's eliminate the options that are counterproductive. Option E, limiting the training to simple descriptions, is the opposite of what you'd want to do. If you want the model to understand detailed prompts, you must train it on detailed prompts. Option D, using a fixed model without fine-tuning, is a passive approach. It's not a strategy for optimizing performance. Option A, using a separate refiner model, can help improve image quality, but it doesn't help the initial model understand the complex text prompt better. If the first model misunderstands the prompt, the refiner will just create a high-quality version of the wrong image. This leaves us with the 2 correct answers, B and C, which form the foundation of any good text-to-image system. Option B is to incorporate a large and diverse set of image-text pairs for training. This is the model's education. For an AI to learn the connection between the words, a photorealistic portrait of a queen from the 18th century, and the visual concepts of that era's clothing, lighting, and portrait style, it must have seen countless examples of similar images paired with rich, descriptive text. The diversity and quality of this training data are what give the model its vast visual vocabulary. Option C is to use a transformer-based model for text encoding. This is the model's reading comprehension skill. When it receives a complex prompt, the text encoder's job is to decipher the meaning and the relationships between all the words. A powerful transformer is what understands that a cat wearing a tiny hat is different from a hat with a cat on it. It translates the nuanced human language into a meaningful mathematical representation that the image generation part of the model can then use to create the picture. So, to build a great text-to-image model, you need a world-class education, a massive, diverse dataset, and excellent language comprehension, a powerful transformer text encoder. Question 29. You are developing a multimodal AI system that integrates image recognition and natural language processing, NLP, to generate product descriptions for an e-commerce platform. During testing, you notice that the system occasionally generates inaccurate or irrelevant descriptions, particularly when processing images with unusual features or text with ambiguous meanings. Which two actions should you take to improve the accuracy and reliability of the system's outputs? Select 2. Implement a robust validation set with edge cases that include unusual features and ambiguous text. B. Disable dropout during training to maintain full connectivity in the model. C. Reduce the model's complexity to simplify the processing of inputs. D. Increase the batch size during training to improve the model's generalization. E. Incorporate a feedback loop where incorrect outputs are reviewed and used to retrain the model. Okay, so the core problem is that our AI is good with standard products but struggles with edge cases, unusual items, or ambiguous descriptions. We need to find two strategies that will make the system more robust and reliable, especially when faced with these tricky inputs. Let's first look at the options that are not the best fit. Option B, disabling dropout, would likely make the model less reliable, as dropout is a technique used to help models generalize better. Option C, reducing the model's complexity, might prevent some strange outputs, but it could also make the model less capable of understanding nuance in the first place. Option D, increasing the batch size, is primarily a way to make training more stable or faster. It's not a direct strategy for improving performance on specific, difficult edge cases. This leaves us with the two correct answers, A and E, which represent a powerful two-part strategy for building a robust AI system. Option A is to implement a robust validation set with edge cases. Think of this as the quality assurance step. If you know the model fails on unusual items, you need to create a specific test for it that is full of those unusual items. You can't improve what you don't measure. By building a tough exam for your AI that includes its known weaknesses, you can accurately track your progress and ensure that any changes you make are actually improving its performance on the things that matter. Option E is to incorporate a feedback loop. This is the continuous learning part. This means that when the AI generates a wrong description in the real world, a human can flag it, correct it, and that corrected example gets added back into the dataset for future retraining. This creates a cycle of improvement where the model literally learns from its own mistakes. Over time, it will see more and more of these difficult edge cases and become progressively better at handling them. So, the best way to improve the system is to combine rigorous testing against its known weaknesses, A, with a mechanism to learn from its real-world failures, B. Question 30. You are working on a project that involves training a multimodal AI model combining natural language processing and computer vision to provide real-time captions for live video feeds. However, the captions generated often lag behind the video. Upon investigation, you find that the language model is causing the delay. Which of the following strategies is most likely to reduce the lag and improve synchronization? A. Increase the video frame rate. B. Reduce the input image resolution. C. Use a more complex language model. D. Switch to a smaller language model. Okay, so this question gives us a very clear problem and a very specific diagnosis. The real-time captions are lagging, and we know exactly why. The language model component is the bottleneck. It's the part that is running too slowly. Our goal is to find the most direct way to fix this specific slowdown. Let's look at the options that don't directly address the identified bottleneck. Option A, increasing the video frame rate, would actually make the problem worse by sending more data to the already struggling system. Option B, reducing image resolution, would speed up the computer vision part of the pipeline, but the question tells us the language model is the problem, so this wouldn't fix the main issue. Option C, using a more complex language model, is the opposite of what we want to do. A more complex model would be even slower and would increase the lag. This makes option D the correct and most logical answer. Switch to a smaller language model. If the language model is the component causing the delay, the most direct way to reduce that delay is to use a model that is faster. Smaller language models have fewer parameters, which means they require fewer calculations and can generate text much more quickly. While there is often a trade-off, a smaller model might be slightly less nuanced or accurate than a larger one. For a real-time application like live captioning, speed is critical. A caption that is 95% perfect but appears on time is much better than a 100% perfect caption that appears 5 seconds too late. Therefore, choosing a smaller, faster model is the most effective strategy to solve the identified latency problem. Question 31. You are working on optimizing the performance of a generative AI model used for multimodal content creation. The model currently suffers from high latency and suboptimal accuracy in its outputs. Your senior team member suggests focusing on computational efficiency and model accuracy. Which strategies should you consider implementing? Select 2. Use a simpler optimizer like stochastic gradient descent, SGD, instead of ATOM to speed up convergence. B. Reduce the batch size during training to decrease memory usage and improve training speed. C. Prune the model by removing less important neurons or layers to reduce the model size and inference time. D. Apply mixed precision training to speed up computations without significantly affecting model accuracy. E. Increase the number of layers in the model to capture more complex patterns and improve accuracy. Okay, so the challenge here is to fix a model that is both slow and not very accurate. We need to find 2 strategies that can improve its speed, computational efficiency, without sacrificing, and hopefully even helping, its accuracy. Let's first rule out the options that don't fit the criteria. Option A, switching to a simpler optimizer like SGD, would likely slow down training convergence, not speed it up. Option B, reducing the batch size, also tends to decrease training efficiency on modern GPUs. Option E, increasing the number of layers, would make the model bigger and slower, which directly contradicts the goal of improving efficiency. This leaves us with C and D, which are 2 very common and powerful optimization techniques. Option C is to prune the model. You can think of this like trimming a bonsai tree. After the model is trained, pruning is a process that intelligently removes the least important connections, neurons, or even whole layers. This results in a smaller, lighter model that is significantly faster to run for inference, directly improving computational efficiency. This is done carefully to have a minimal negative impact on accuracy, and in some cases, can even help it by removing noise. Option D is to apply mixed precision training. This is like doing math with slightly rounded numbers instead of long, exact decimals. For many calculations during training, you don't need 32-bit precision. Using lower 16-bit precision is much faster on modern GPUs with tensor cores and also uses less memory. This technique is specifically designed to provide a major boost to computational efficiency without a significant drop in the model's final accuracy. Both pruning and mixed precision are excellent strategies for making a model more efficient while preserving its accuracy, which is exactly what the question asks for. Question 32. You are deploying a multimodal AI system that integrates text, images, and voice commands to assist in autonomous driving. The system must make real-time decisions based on input from various sensors in different environments. Which strategy best ensures that the AI system remains reliable and trustworthy in diverse driving conditions? A. Prioritizing the speed of decision-making over the accuracy of sensor interpretation. B. Using a generic AI model without customizing it for different environments. C. Relying solely on data collected from one geographical region to train the AI system. D. Utilizing NVIDIA's Drive platform to simulate and test the AI system in various real-world scenarios before deployment. Okay, this question deals with a safety-critical application, autonomous driving. The most important words here are reliable and trustworthy. We need to find the strategy that best ensures the AI will be safe and predictable under all sorts of conditions. Let's start by eliminating the options that are clearly dangerous or irresponsible. Option A, prioritizing speed over accuracy, is a recipe for disaster. A fast wrong decision in a car can be fatal. Accuracy and safety must come first. Options B and C are similar problems. They both describe building a naive AI. Using a generic model, B, or training on data from only one region, C, is like teaching someone to drive only in an empty parking lot on a sunny day. That driver would be completely unreliable and untrustworthy in a busy city during a snowstorm. A reliable system must be trained and tested on diverse data from diverse environments. This makes option D the best and most responsible engineering approach, utilizing NVIDIA's Drive platform to simulate and test the AI system. Think of this like a flight simulator for an airline pilot. Pilots practice emergency situations like engine failures and bad weather thousands of times in a safe, virtual environment before ever flying a real plane with passengers. The NVIDIA Drive platform is the flight simulator for self-driving cars. It allows developers to create and test the AI against millions of miles of virtual driving, including rare and dangerous edge cases like a child running into the road or a sudden blizzard. It's impossible and unsafe to test all of these scenarios in the real world. By rigorously testing and validating the system in a massive, diverse set of simulated scenarios, you can build the confidence and proof needed to ensure the AI will be reliable and trustworthy when it's finally deployed on a real road. Question 33. Which of the following best describes how a pre-trained modern LLM can be leveraged to solve various NLP tasks such as token classification, text classification, summarization, and question answering? A. Pre-trained LLMs are only useful for text generation and cannot be adapted to tasks like token classification or summarization. B. A pre-trained LLM can be fine-tuned on specific datasets to perform token classification, text classification, summarization, and question answering with high accuracy. C. A pre-trained LLM must be used in conjunction with RNNs to achieve effective text classification and summarization. D. Pre-trained LLMs require manual feature engineering to perform tasks such as token classification and summarization. Okay, so this question is really asking about the magic of modern LLMs. How can one single massive model be so versatile and able to handle so many different language-related jobs? Let's start by eliminating the incorrect statements. Option A is simply false. LLMs are incredibly flexible and can be adapted for much more than just text generation. Option C is also incorrect because modern LLMs are based on the transformer architecture, which largely replaced older architectures like RNNs. You don't need to add an RNN to them. And option D is the opposite of reality. One of the biggest advantages of modern LLMs is that they eliminate the need for tedious manual feature engineering by learning features directly from the text. This leads us to the correct answer, option B. A pre-trained LLM can be fine-tuned on specific datasets to perform these various tasks. This describes the core concept of transfer learning, which is fundamental to modern NLP. Think of a pre-trained LLM as a very smart university graduate who has read millions of books and has a vast, general understanding of language and the world. This is the pre-training stage. Now, you want this graduate to get a specific job. If you want them to be a legal assistant, text classification, you give them some specific legal documents to study. If you want them to be a medical writer, summarization, you have them practice summarizing medical journals. This extra specialized training on a smaller, task-specific dataset is called fine-tuning. It takes the massive general knowledge the model already has and adapts it to excel at one particular task. This process is why a single foundation model can be leveraged to achieve state-of-the-art performance on a wide variety of different NLP tasks. Question 34. To enhance the trustworthiness of an AI system used for healthcare diagnostics, Which approach involving NVIDIA technologies is most appropriate? A. Using NVIDIA GPUs to increase the speed of diagnosis without focusing on data security. B. Prioritizing the collection of large amounts of patient data over maintaining patient privacy. C. Implementing NVIDIA Clara's privacy-preserving federated learning to train the AI on sensitive patient data across multiple institutions without sharing the data. D. Training the AI solely on data from a single medical institution to streamline the process. Okay, this question is about building a trustworthy medical AI. In a field like healthcare, trustworthiness has two critical components. The AI must be accurate, and it must rigorously protect patient privacy. The challenge is that to make the AI accurate and unbiased, you need lots of diverse data from many different hospitals, but privacy laws prevent those hospitals from sharing their sensitive patient data. Let's look at the options that fail to solve this problem. Options A and B are immediately wrong because they suggest ignoring data security and patient privacy. In healthcare, this is unethical, illegal, and would completely destroy any trust in the system. Option D, training on data from only one hospital, would result in a biased model that isn't reliable or trustworthy when used at other locations with different patient populations. This makes option C the correct and most sophisticated solution, implementing NVIDIA Clara's privacy-preserving federated learning. This technology is designed to solve the exact dilemma we just described. Here's how it works with an analogy. Imagine you want a model to learn from the secret patient files at 10 different hospitals. The hospitals can't send you their private files. With federated learning, instead of bringing the data to the model, you send the model to the data. The AI model travels to Hospital A and learns from its data, right there on the hospital's secure servers. Then, only the mathematical learnings, not the data itself, are sent back to a central location. The model does the same at Hospital B, Hospital C, and so on. The central server then aggregates the learnings from all 10 hospitals to create a single, powerful model that has learned from a diverse, multi-institutional dataset without any sensitive patient data ever leaving its original, secure location. NVIDIA's Clara platform provides the specific tools to enable this process, making it the best approach to build a highly accurate and trustworthy medical AI that respects patient privacy. Question 35. Which of the following is not a typical application or benefit of using UNet architectures in generative AI, particularly within the context of image generation and manipulation? A. Image inpainting and super-resolution tasks. B. Facilitating efficient feature extraction and upsampling for detailed image generation. C. Image segmentation and pixel-wise classification. D. Medical image analysis such as tumor detection. E. Encoding high-dimensional text data for multimodal embeddings. Okay, this is a which one of these is not like the others type of question. To answer it, we need to know what a UNet is and what it's good at. A UNet is a specific type of neural network architecture designed for images. Its superpower is taking an image as input and producing another image of the same size as output, where every pixel has been intelligently modified. It's famous for its skip connections, which help it remember very fine-grained details from the input image while it's creating the output image. This makes it excellent for any task that requires precise pixel-level detail. Now let's look at the options. Options C and D, image segmentation and medical image analysis, are the classic use cases for UNet. In fact, it was originally invented for segmenting biomedical images. Segmentation means classifying every single pixel, e.g., this pixel is a tumor, this pixel is healthy tissue, which is exactly what UNet excels at. Option A, image inpainting, filling in missing parts, and super resolution, increasing detail, also fits perfectly. Both tasks require generating a new, detailed image based on an original, which is a perfect job for a UNet. Option B is just a technical description of how a UNet works. It has an encoder path for feature extraction and a decoder path for upsampling, and it does this efficiently to generate detailed images. So this statement is true. This leaves us with option E, encoding high-dimensional text data for multimodal embeddings. This is the correct answer because it's the one thing on the list that has nothing to do with UNet. UNet is an architecture for images, grid-like data. Encoding text is the job of natural language processing models, which are typically based on the transformer architecture, like BERT or GPT. Using a UNet to process text would be like using a high-end photo editor to write a novel. It's completely the wrong tool for the job. Question 36. Which statistical method is most appropriate for evaluating the agreement between multiple human annotators labeling images with severity scores on a scale of 1 to 5 for a multimodal medical imaging application? A Krippendorff's alpha. B. Spearman's rank correlation coefficient. C. chi-squared test. D. Pearson correlation coefficient. E. Cohen's kappa. Okay. The core of this question is about measuring inter-annotator agreement or inter-rater reliability. Essentially, we have several doctors looking at the same X-rays and giving them a severity score, and we want to know how consistently they agree with each other. The key constraints in the question are that we have multiple annotators, more than 2, and the scores are on an ordinal scale, 1 to 5, where the order matters. Now let's look at the options. Options B, C, and D are used for different purposes. The chi-squared test, C, checks for an association between variables. It doesn't measure agreement. Pearson correlation, D, measures the linear relationship between two continuous variables, which isn't what we have here. Spearman's correlation, B, works for ranked data, but like Pearson, it's designed to compare only two variables, or in this case, two annotators. So these are not the best fit. This leaves us with Cohen's kappa and Krippendorff's alpha, which are both used to measure agreement. Option E, Cohen's kappa, is a very common and useful metric. However, the standard version of Cohen's kappa is specifically designed to measure agreement between only two annotators. Since the question specifies multiple human annotators, Cohen's kappa is not the most appropriate choice. This leaves us with option A, Krippendorff's alpha. This is the correct answer because it is an incredibly flexible and robust measure of agreement. Its main advantages are that it can handle any number of annotators. It works perfectly with ordinal data, like our 1 to 5 scale. And it can even handle situations where some annotators didn't label every single image, missing data. It is designed for exactly the kind of complex, real-world annotation scenario described in the question, making it the most appropriate statistical method. Question 37. You're developing an Avatar Cloud Engine, ACE, application to create a real-time, interactive virtual assistant. The assistant needs to respond to user speech, understand their intent, and generate appropriate responses. Which sequence of NVIDIA SDKs would provide the most complete solution for this task? A. Triton Inference Server, for serving all models, Riva, for speech recognition and synthesis, ACE, for avatar rendering and animation. B. Riva, for speech recognition and synthesis, Triton Inference Server, for serving a pre-trained chatbot model, ACE, for avatar rendering and animation. C. Nemo, for training a custom language model, Triton Inference Server, for serving the trained language model, ACE, for avatar rendering and animation. D. CUDA, for running deep learning workloads, Riva, for speech recognition and synthesis, ACE, for avatar rendering and animation. E. Riva, for speech recognition and synthesis, Nemo, for natural language understanding and response generation, Triton Inference Server, for model deployment, ACE, for avatar rendering and animation. Okay, this question is asking us to assemble a complete toolkit to build a virtual assistant. We need to find the option that includes all the necessary pieces: the ears to listen, speech recognition; the brain to think, language understanding and response generation; the mouth to speak, speech synthesis; and the face to animate. Now let's look at the options. Many of the options are incomplete. Option C is missing the ears and mouth. It can think, but it can't handle speech. Option D is also missing the brain. It can listen and speak, but it can't understand or formulate a response. Option B is getting closer, but it just mentions a generic pre-trained chatbot model without specifying the framework used to build and customize that brain, which is a key part of the solution. This leaves us with option E, which is the correct answer because it describes the most complete, end-to-end pipeline for both developing and deploying a custom virtual assistant. Let's break down its components. Riva provides the ears and mouth. It handles the automatic speech recognition, ASR, to understand the user's speech and the text-to-speech, TTS, to generate the spoken response. NeMo is the framework for building the custom brain. It's used for the natural language understanding, NLU, to figure out what the user wants and the response generation to decide what to say back. Triton Inference Server is the high-performance engine that runs the brain. Once you've built your model in NeMo, you use Triton to deploy it so it can handle requests quickly and efficiently. ACE is the final piece, providing the animated face that brings the character to life. This option is the only one that covers the entire workflow. The speech interface, Riva, the custom intelligence, NeMo, the high-performance deployment, Triton, and the final animation, ACE. Question 38. Which of the following evaluation metrics is most appropriate for assessing the performance of a multimodal generative AI model that generates image captions based on images and audio descriptions? A. BLEU, Bilingual Evaluation Understudy. B. Perplexity. C. Root Mean Squared Error, RMSE. D. Inception Score. E. Mean Squared Error, MSE. Okay, the key to this question is to focus on what the model is producing. The model's final output is an image caption, which is a sentence of text. So, our job is to find the metric on this list that is specifically designed to measure the quality of a machine-generated sentence. Now let's look at the options. First, we can eliminate the ones that are for the wrong data type. Options C and E, RMSE and MSE, are used to measure the error in predicting numbers, like the price of a house. They are completely unsuitable for evaluating text. Option D, the Inception Score, is a metric used to evaluate the quality and diversity of generated images, not text. This leaves us with Perplexity and BLEU. Perplexity B is a metric that evaluates how well a language model is at predicting a sequence of text. While it's useful for understanding the quality of the language model itself, it's not the most direct way to compare a final generated caption to a ground truth human caption. This leaves us with option A, BLEU. This is the correct answer. The BLEU score was originally created for machine translation to see how closely a machine's translated sentence matched a human's translation. It works by comparing the n-grams, sequences of words, in the generated text to the n-grams in one or more high-quality reference texts. Because image captioning is also a task of generating a sentence that should match a human-written description, BLEU is a very common and appropriate metric to use. Question 39. You are training a multimodal generative AI model that takes text and images as input to generate videos. During experimentation, you observe that the model performs well on common scenarios, e.g., a dog playing in the park, but struggles to generate coherent videos for less frequent or abstract scenarios, e.g., the concept of time flowing. What is the most effective strategy to improve the model's performance on these challenging scenarios, focusing on test data quality? Implement data augmentation techniques on the existing training data, focusing on color adjustments and minor image transformations. B. Increase the size of the training dataset by duplicating existing common scenario examples. C. Reduce the complexity of the model architecture to prevent overfitting on the common scenarios. D. Train the model for a significantly longer duration on the existing training data. E. Curate a new test dataset specifically containing challenging scenarios and use it to evaluate and fine-tune the model. Ensure the new test data includes diverse interpretations and variations of the abstract concepts. Okay, the key issue here is that our AI model is like a student who is great at the easy, concrete problems but fails when it comes to the hard, abstract ones. Can handle a dog in a park because it has seen many examples of that, but it has no idea how to represent the concept of time flowing because it lacks the right learning materials. Now let's look at the options. First, let's eliminate the strategies that won't work. Option B, duplicating the easy examples, and option D, training longer on the existing data, are like giving the student more of the same easy homework. This will only make the model better at the common scenarios and won't teach it anything new about the abstract concepts it's failing on. Option A, simple data augmentation like color adjustments, won't teach the model a new concept. It just creates minor variations of what it already knows. Option C, Reducing the model's complexity would likely make it even harder for the model to grasp a difficult abstract idea. This leaves us with option E, which is the correct and most effective strategy. It's a methodical, two-part approach to solving the problem. Curate a new dataset with challenging scenarios. This is the most important step. You can't expect the model to learn about abstract concepts if it has never seen examples. This step involves actively gathering or creating a high-quality collection of data that represents these difficult ideas in various ways. Use it to evaluate and fine-tune the model. Once you have this new, specialized dataset, you can use it to specifically teach, fine-tune the model. By training on these targeted examples, the model finally gets the information it needs to learn how to handle these challenging and abstract scenarios. In short, to teach a model a new and difficult concept, you must first provide it with a high-quality textbook on that subject, the curated dataset, and then give it time to study, the fine-tuning. Question 40. A developer wants to build a system that can classify images into a set of new, arbitrary categories, e.g., a photo of a dog on a skateboard, a drawing of a cat in a hat, without having to train or fine-tune the model on those specific categories. Which of the following best describes the core mechanism that allows the CLIP model to perform this kind of zero-shot image classification? A. The model first generates a detailed caption for the image, and then uses a separate NLP model to match the caption to the closest category. B. The model uses a fixed classification layer that has been pre-trained on over 1,000 common object classes. C. The model uses an object detection component to find all objects in the image, and then classifies the image based on the most prominent object. D. The model encodes the image and all the text categories into a shared embedding space, and then identifies which text embedding has the highest cosine similarity to the image embedding. E. The model is rapidly fine-tuned on a small set of examples from the new categories before it makes a prediction. Okay, this question is digging into the magic of CLIP, its ability to perform zero-shot classification. This means it can correctly categorize an image even if it has never seen that specific category during its training. The question asks for the core mechanism that makes this possible. Now let's look at the options. First, we can eliminate the options that describe other types of learning or tasks. Option E describes few-shot learning or fine-tuning, which is explicitly what zero-shot classification is not. Option A describes a captioning then classifying pipeline, which is not how CLIP works. It's a matching model, not a generative one. Option C describes object detection, but CLIP classifies the entire image based on its overall content. It doesn't detect individual objects. Option B describes a traditional classifier with a fixed set of categories, which is also the opposite of what a flexible zero-shot model does. This leaves us with option D, which is the correct answer. This describes the fundamental process of CLIP. Think of CLIP as a universal translator that can map both images and text into a single, shared, meaning space, the embedding space. Here's how it works. Image encoding. The image encoder looks at the input image and creates a vector, a list of numbers that represents its semantic content. Text encoding. The text encoder takes all the potential text categories, e.g., a photo of a dog, a photo of a cat, and creates a unique vector for each one. Similarity comparison. The model then calculates the cosine similarity, which is basically a measure of how similar two vectors are, between the single image vector and all of the text vectors. The text category whose vector is closest to the image vector in the shared space is chosen as the prediction. This simple but powerful mechanism allows CLIP to classify images into any set of categories you can describe with text, making it incredibly versatile. Thanks for watching. If you found this video interesting and helpful, please like, share, and subscribe to our channel. See you in the next video. Happy learning!